Hey guys, today we're going to learn about how to do vector addition of electric fields specifically. Alright, now let me take you back to first semester when we first started about the whole idea of vector addition, right? So it could be things like a troop of Boy Scouts walk, say, like this, whatever, 5 miles at some angle. And then they, do this and then some of that, right? And what you did with those individual vectors was you broke them down into components. Ta-da! X and Y for that one. Let's see, for this one we have X component, Y component, and then we had, again, an X component and a Y component, right? Which, of course, we call I and J, all right? And then you took those individual components and you added up all of the i's, and then you added up all of the j's. And the way that that usually went involved using the sine and cosine functions. All right, so more or less when we do vector addition of electric forces or fields, it's going to be kind of the same thing. You got to figure out the I and j components, and then you add up the i's, you add up the j's, and then the result is the total electric force or electric field. For this video, we're mostly going to deal with electric forces. We'll talk about electric fields on a later date. Okay, so the notation for that looks often a little bit different for electric fields. Really not for necessarily any good reason. So I keep saying electric fields, I mean forces. So the formula for electric force, if you recall, is KQQ over R squared R hat. Ooh, what is the R hat? All right, so we may have kind of glossed over it on other occasions, like, if you only want to know the force that two particles exert on each other, it doesn't necessarily matter what direction that is in. All right, but if you, say, have 3 charges arranged in a triangle and you want to know the force on the one at the top of the triangle, then you have to worry about directions. And that's what R hat is all about. R hat is cosine theta I plus sine theta j. In other words, it's the components, right? If you had this vector here was like, I don't know, 5 meters at 37 degrees, or whatever it may happen to be, the trig function that you would use to get the I component, or the X component, would be the cosine function, because cosine relates the hypotenuse and the adjacent side, right? Cosine is adjacent over hypotenuse. So if you did, 5 cosine 37, that would give you this bottom side. Okay, so the X component, the I component, is related to the cosine function. All right, and then same idea for the J component. Sine theta relates to the J component. So really all the R hat is just a different way of writing out the components. It's sort of a shorthand for writing that. All right, so if then you are presented with a force vector addition problem for electric fields, a lot of the time, you're going to use the R hat presented like this and express the components that way. All right, so let's look at an example problem, just so you can sort of get the basic idea here. Find in your notes packet example 2, I think it is. Oh, I'm shuffling papers. Okay, example 2. It's got, I'll obviously draw it in the video because that would be silly otherwise. It says we've got a plus Q. All right, way over here we've got another plus Q. And then up here, a minus Q. All right, and this distance is D, and both of these distances are root 3D. Okay, so always, just like the problems that we've done before, where things are just on a line, where we don't have to worry about components because nothing's at angles. Everything's either right or left, or up or down, right? Similarly, though, we have to start off by drawing the directions of all of the forces that are acting on each of the charges. The reason why you've got to do that is when you do your components, sometimes I components or J components will add, and sometimes they will subtract. All right, so say we're looking at the forces on the negative Q. The plus Q and the minus Q will attract each other. There we go. So maybe we'll call that force 1, 2, because I'll number these two charges 1 and 2. All right, so that's force 1, 2, whatever. All right, and then same story here. Those ones are going to attract. So maybe we'll call that F2, 3, because this will be charge number 3 down here. All right, now the reason you would need to do that in the first place is to decide whether or not those forces add or subtract. All right, well now, because they aren't directly on a line, you can't just be like, yeah, they add or they subtract. Neither one of those answers is quite right. Instead, you'd have to talk about, look, they're both down, so therefore the J components will add and both be in the negative J direction. Whereas the I components are going to subtract because they're in opposite I directions. All right, so the I's would subtract, the J's would add, and both be in, say, the negative direction. All right, for completeness, the question asks you for parts A and B to also draw the forces that act on the plus Q's. And so those would look like they're going to be repulsive. All right, they repel each other. All right, so those would be all of the various forces. All right, the next part, part C, wants us to determine the total force on, it says, on the left plus Q. So I guess I do need to name this force here F13. All right, and we'll have to come up with an expression for the magnitude of the force on it, and then determine each of the components acting on it. This is maybe not maximum complicatedness, but this is one of the harder vector addition problems, mostly because there's no easy shortcut. Okay, so in a later video, you'll get to see a problem where there is a shortcut. Right? Actually, when we get to number 2, we'll talk about how there's actually sometimes a shortcut. Okay, so be that as it may, what we're going to do right now is start writing out expressions for each of those forces. The only equation that we've got so far this unit is F equals KQQ over R squared, R hat. Okay, so the very first thing then is going to be to plug in values for Q and Q and for R. Let's do the F13 first, which I'm picking because it's in a straight line, okay, rather than at an angle. Okay, so pause and figure it out on your own, and then resume the video when you think that you have an appropriate expression for it. So this is what I plugged in. The numerator here is going to simplify to KQ squared. Let me do that. I'm going to deal with the R hat in a little bit. And then 2 root 3D squared. All right, 2 root 3 because it's the whole way across. And then you've got to be careful to make sure that you square the whole thing. A lot of the time people like only square the D and forget about the 2 root 3 part of it. So if I correctly square that, that'll come out to 12D squared. Okay, now next, the R hat thing. If you have something like this force, then you're going to have both an I and a J component, right? Because it goes to the right and also up, so it's going to have some of each. Whereas this one, just looking at it, you can see the J component is going to be 0. I don't need to mess around with definitions of trig functions if I don't have to. In this case, I don't have to, so I won't. I'm going to say 0 for the J component. And for the I component, there is nothing about a problem which will set up the signs for you. You always have to stop and think, is that going left, right, up, down, what's it doing? In this case, it's going left, so the I component would be negative. All right, well, what would I do about the cosine theta part of it? All right, again, if it's going directly along an axis, you don't have to mess around with the angles and getting literal and stuff, okay? It's 100% in the I direction. So the I component for that one is really just -1. So that's all I would have for that. It goes directly to the left. The entire magnitude of the electric force is directed that way. So I can just say -I, all that stuff. All right, so that's good for F13. Now we need to get F12. All right, so see if you can work it out a little bit, get the expression here for the magnitude. And again, we're going to pause and then talk about how to deal with the r hat part of it. Okay, so we worked out that the distance that the two charges are separated from each other is 2d. Turns out this is a reference triangle you ought to know. It's technically a 30, 60, 90 triangle, but we're actually going to pretend we don't know that for going to the cosine and sine. As I will discuss on many occasions, you don't actually have to know what the angle is to come up with an expression for the sine or cosine. Be that as it may, we do need, though, to get a correct distance. So, even if you didn't recognize the triangle, you could do Pythagorean theorem and determine the distance for the hypotenuse. Okay, so 2d, we get it all squared. So this part, just like this part, is what you would refer to as the magnitude of the force. Now we've got to get components for that force. All right, so the components are defined as, cosine theta I plus sine theta j. Great. Most of the time what you will do to get those is go back to the definitions of cosine and sine. So cosine is defined as adjacent over hypotenuse. Sine is defined as opposite over hypotenuse. So what you will do with your diagram is directly on it, draw which angle you're talking about. Always pick an angle from the horizontal. There's an angle from the horizontal. The next thing that you're going to do is to find the I component of the force is you look at the adjacent and the hypotenuse. So there's the adjacent side, root 3d. The hypotenuse is 2d. So that means that root 3d over 2d, which simplifies to root 3 over 2, is the value of cosine theta. I do not care what theta is. I realize it's technically 30 degrees. Okay, doesn't matter. What I care about is the value of cosine theta, and you won't always actually be able to nail it down to a particular number. For example, later on you might see problems where they're like, this distance here is y and this distance is d. Okay, well you could do Pythagorean theorem, come up with an expression and stuff, but for getting like sine or cosine for something like this, you're not going to get an angle. You're going to have to instead say something like cosine theta is d over square root of d squared plus y squared, or something like that. Okay, so cosine theta is going to be root 3 over 2, and let's stop and check if it's in the positive direction. Looks like it is because of the direction I drew that arrow. All right, so we're all set there. For sine, it's opposite over hypotenuse, so that's going to be d over 2d. So that would be 1/2. And again, stop and check the sign, right? My force 1, 2 arrow is drawn like this. That's in the positive j direction. So we'll say plus. All right. Now, at this point, actually, the most annoying thing to do is now simplify this expression. So I will let you look at the notes packets to do that. But the approximate story is add up the I components, add up the j components, if there is another j component, and you'll have some kind of a simplified expression for it. And if they're numbers, then so be it. You can also look in the notes packet for the worked out answer for the total force on the negative q, or watch one of my other example videos. Okay, hope that was helpful.